All right, let's continue our discussion in acoustics and discuss a very important phenomenon that has to do with waves more generally, but of course, sound waves are part of that, and that is interference. It turns out that when waves, let's say two different waves, meet at a particular location, they can interfere with each other. They can either increase the size of the wave or decrease the size of the wave depending on how they meet. So for instance, say we have a wave, looks like this, and then we have some other wave coming in, and let's say it also has exactly the same frequency and wavelength, and so it's going to basically go over top of the other one just like that. So we have two different waves going through the same location at the same time. Their peaks match, their valleys match, they have the same frequency and wavelength and all of that. What does it mean? It means that at every single point on this wave, the amplitudes add together. And so the black wave and the blue wave would add, in this case, constructively interfere. And we'd have a wave which is twice as big. Now it has the same exact frequency, same exact wavelength, but the amplitude is just larger now. If this was water waves, then the two water waves, let's say they're only 1 foot high each, when they meet, they would add together and become a 2 foot high wave instead. Now, of course, the exact opposite can be true. We can have two waves. Let's say we have this wave like this. And then we have another wave which is the same frequency and wavelength, but this time shifted by some phase. That is to say, when the peak of one of the waves hits the valley of another wave. Something like this. Okay, so they're just out of phase by 90 degrees, or they're out of phase completely here. And so that means that all the times this black wave is going upwards, the blue wave is going downwards. And vice versa. As the blue one goes up, the black one goes down. And if these two waves have the same amplitude, same size of a wave, and same frequency and all of that stuff, then the two waves would completely destructively interfere. And so you would get nothing. Absolutely no wave whatsoever. Because as much as one goes up, the other comes down, they subtract off of each other, and you get nothing. And of course, you can have any situation in between. You can have one of the waves have a different frequency, and so maybe it's waving like this, and in the blue wave, maybe it's got a completely different frequency, so it goes like this. So you don't have some perfect matching of peak with peak and valley with valley, or exactly interfering with each other destructively or anything like that. You have something in between. And so maybe in this case, you'd get at the very beginning, these two are adding together, getting bigger, but then the black one starts to die off, and then the blue one starts to die off with the black one. And of course, my drawing here is pretty bad. It's definitely not correct, but something like that. They interfere with each other in such a way that it's not perfectly adding together, constructive, not perfectly destroying, destructive, but something in between, and so you get some other wave, which is a combination of those two waves, the superposition principle. So we want to use this fact to try to figure out something, calculate some issues that may arise in acoustics. For instance, let's say we're playing some music in a room, and we have stereo. Let's say we have a speaker over here and a speaker over here. And let the distance between these two speakers, let's say, is 3.2 meters. It's a very specific number I'm choosing. You'll see why, of course. And then we have where we're seated in the room. Maybe we're seated right here. And this distance from here to here, from the right side speaker to us, is 2.4 meters. And so our speakers are playing a specific note. Let's say it's not a full symphony, it's not a full song, but rather just a particular sound is being produced. A single note is being produced by the speakers. And we're trying to listen to it at our location here, us. What I'd like to know is, can I figure out what will happen? Will the waves coming from each speaker constructively interfere or destructively interfere? That is to say, depending on the frequency of the sound being played, it's possible that when the sound gets to us in this yellow part, I'll do blue and green, the wave coming from the blue speaker gets to us, and a wave coming from the green speaker gets to us. And by the time they both get to us, they're going to interfere with each other. But can they interfere with each other and amplify so it sounds louder than normal? Or can they interfere in such a way that they destructively interfere so you actually don't hear anything? Or somewhere in between? How would we figure something like this out? Because this is definitely something that must be paid attention to if you're designing an auditorium or an amphitheater or something like that. The acoustics in the room, you have to pay attention. There may be blind spots where if a person stands at a very specific location, it just so happens that particular notes will destructively interfere and that person won't hear anything coming from the speakers or the instruments or whatever's being played. But maybe for a different frequency, he will or she will hear something. So let's do this particular example then. We will say that the speakers are playing a frequency of 214 hertz. Okay? So I've got 214 hertz sound coming from each of these speakers, and I want to know when that sound gets to us, will we have constructive or destructive interference, or neither? It's possible to have neither. What kind of interference? Will we get? Well, here's what you have to know. If we go back and look at the waves, notice when they constructively interfere, then every time we have a peak, the other wave has a peak as well. And whenever we have a valley, the other wave has a valley. And in that case, the waves are adding to each other and getting louder. Whereas destructive, the exact opposite is true. When one has a peak, the other has a valley. What does that mean? That means one of the waves is shifted by 90 degrees, or pi over 2, depending on your units. That is to say, the blue wave, this blue wave here, is 1/2 of a wavelength off of the black one. If the black one is going upwards, the blue one would like to be going upwards, but it's not yet. The upwards part is right there. It's a 1/2 a wavelength to behind, or to ahead, whichever way you want to think about it. And so what makes something constructively interfere versus destructively is if the two waves constructively interfere if they're exactly some multiple of one wavelength apart from each other. So if they're exactly on top of each other, you get constructive interference. If the blue wave is a whole wavelength ahead or behind, well, it still looks like they're on top of each other. However, if the blue wave or the black wave is 1/2 a wavelength off, that means one of the waves is going up while the other is going down. And then in the middle, so neither constructive or destructive, is when you have something other than either a full integer multiple or a half integer multiple. So given that, in order to solve this problem, all we have to do is say these two waves will constructively interfere if by the time both waves reach the observer, they have traveled a distance, or I should say the difference, let me write it like this, I'm sorry. By the time both, I'll say it as like this. These two waves will constructively interfere if the difference in their travel path is an integer multiple of the wavelength of the sound. Okay, so the blue wave is going to get to us. It's going to travel a certain distance. The green wave will get to us. It's going to travel its own distance. If the difference between those two paths is some integer multiple of the wavelength of that sound, they will constructively interfere. And of course, likewise, if these two waves will destructively interfere, it's because the difference in their path length must be a half integer multiple. So everything the same, destructively interfere if the difference in path length is a half multiple of the sound's wavelength. All right, so let me rewrite it on the next page so it'll be a little cleaned up. Here's our example. We have, let's say, the green source. We've got the blue source, and then we have us. This blue wave is going to reach us. The green wave is going to reach us. And what we know is that the distance between the speakers is 3.2 meters. And the distance from the blue speaker to us is 2.4 meters. And the frequency of the sound is given as 214 hertz. All right, so how do we solve this problem? Well, the first thing we need to do is find the path length difference. That is to say, how much further does this green wave have to travel to get to us than the blue? Well, we know the blue, L for the blue, that's 2.4 meters. That's how far he's going to go. That's easy. That's given in a problem. The green path length, well, that's not given directly. However, we can use Pythagorean theorem. We could say the green length, that's going to be the square root of x squared plus y squared, so 3.2 squared plus 2.4 squared. And that's equal to 4. All right, so we know how far the green wave has to travel. We know how far the blue wave has to travel. What's the difference? Delta L is going to be L green minus L blue, which is 4 minus 2.4, which is 1.6 meters. So that's how much further this green wave had to travel. So it's shifted by some amount. By the time it reaches us, where it is in its wave, up and down and stuff like that, is going to be different than where the blue one is, because it took longer to get to us. It had to go a further distance. Now what we want to do is see, does this path length difference amount to a constructive interference, a destructive interference, or somewhere in between? So now we say, is delta L, is it some n times lambda, or is delta L some n over 2 times lambda? And if it's neither of these, then of course it's somewhere in between. But if it's some n times lambda, that's constructive. And if it's some n over 2 times lambda, that's destructive. Well, in order to do this, of course, we need to know what the heck is lambda. So find lambda. Well, we know V is frequency times lambda from waves. So lambda is V over F. This is sound, so the velocity of sound is 343. The frequency was given as 214. So I divide these, 343 over 214, and I get a number which is 1.6028. Okay. Now I know my lambda. That's the wavelength of this sound. So now I'm going to compare it to my delta L, my path length difference. So that is to say, I'm going to divide delta L over lambda, delta L, sorry, over lambda, and I'm going to see, do I get some integer multiple? Is delta L over lambda some n, some integer n? Or is it some n over 2? Is it like 3 halves or 5 halves or 35 halves or something? Or is it some weird decimal like, well, 1.342, not exactly an integer or a half multiple? So we put 1.6 divided by 1.6028, and this is very, very close to 1. Of course, with some rounding and the numbers aren't perfect and everything, but it's basically 1. So I got an integer as my answer. It could have been 3, it could have been 15, it could have been 130, but it's an integer, or at least it's close enough to being an integer. So I would say this constructively interferes. Now if instead I found that my path length difference was maybe 3.2, then I would divide 3.2 by 1.6028, and I'd get 2, or 1.9965, blah, blah, blah. Again, that's an integer multiple. So that would also be constructive interference. As long as it's an integer, it's constructive. Now, if it's the answer you get is 1.5, 2.5, 17.5, whatever, then that's totally destructive interference. Okay? So these are interference problems. At the end of the day, what do you need to do? Number 1, you can find the path length difference between the sources. Number 2, you find the wavelength for the sound. Number 3, compute the ratio delta L over lambda. And then if it's some integer multiple, it's constructive. If n is half integer, it's destructive. And of course, if it's somewhere in between, if it's 1.3 or something, then it's neither constructive nor destructive. But that's how you figure out whether two waves, and we're doing it in the context of sound, will interfere constructively or destructively. So I hope that was helpful. If you have any questions, of course, you're free to send me an email, come by my office. I'll be happy to help. But I'll see you next time.